intelligence, like intelligence of human beings, is a continuum. You can get a varying degree of intelligence. And so taking this back to the earliest form, arguably, of an intelligence engine, we go back as far as the 1980s, because we have been using what people are referring to as big data these days for decades. And we started that on the early RB211 engines, when we pioneered engine health monitoring, getting data from inside of the engine, understanding pressures, temperatures, shaft speed and vibrations, to better understand how the engine was operating. But it was an early form of EHM, and we weren't really using that data prognostically, we were using it diagnostically. And if you consider the world of product and service, they were very much separate. What do I mean by that? I mean in the sense of we weren't providing a long-term service agreement, we effectively sold the product, and then when the product needed some form of maintenance intervention, we would help the airline by selling parts or overhaul capability to get that product back into serviceable condition. We didn't combine the product and services package. But if we fast forward to the 1990s, with the advent of the Trent family, we also introduced total care, and that turned the world of servicing of aero engines completely on its head. Because one of the characteristics of the first model that I spoke about, where the product and service was different, was you had fundamental conflict of interest between the original equipment manufacturer on the one hand, who effectively wanted the product to break so we could sell spare parts, and the airline who didn't want the product to break so they could keep the engine on wing for as long as possible. This, in the 90s, turned that on its head because we charged airlines $1 per engine flying hour, so our interests were aligned. So the product and the service package started to come together and be linked for the first time. And the ability to, as we fast forward to today, progressively through each increasing member or new member of the Trent family, we've introduced the amount of, increased the amount of data we're taking off these engines, being even more sophisticated in how we prognostically administer these total care risk transfer programs to the benefit of our customers. The logical conclusion of this coming together of these three worlds is effectively a complete overlap. It gets really, really difficult to extricate one from the other. What is a digital technology versus a service versus what is the digital technology within the product? Is the product a service package? The point is, this is how we're thinking, to bring these three worlds together and not lead to a set of characteristics which we see as the three C's. And I'll come to those in a minute, but this is in terms of what the vision of the intelligent engine is, why are we doing it? It's all about helping to deliver passengers more reliably and more efficiently. And the two key outcomes we are chasing are increased efficiency of the asset or increased availability. Which sounds a bit of a buzzword, but what it really means is that the product is doing what it needs to be doing as often as the airline needs it to. So we're minimising disruption, maximising availability. The characteristics of an intelligence engine then, the three C's. Easy to remember: connected, contextually aware, and comprehending. By connected, we mean that it's connected to all other engines, not only within its own fleet, but within the airline and us as an OEM, our ecosystem. So we're able to better get data from the fleet of engines and utilise that through a multiplier effect across all the engines in the fleet. So one engine's experience that we learn from can pretty much instantaneously be applied as a learning to all the other engines in that fleet. Contextually aware is split into two halves, really. One of which is happening today, the other which is slightly more visionary and leads into the third C of comprehending. The first element is our, at Rolls-Royce, as the OEM, being more aware of the context in which the product's operating. The easiest way to think about that is broadening a virtual pipe of data from being one that takes data from inside the engine to a pipe that's bigger and takes data from outside of the engine as well. So we understand and know in what context that engine's operating, whether it be how the pilot's operating it, what weather the engine's experiencing, or things like what's the level of sulfur in the atmosphere that engine is flying through, and therefore there is a better understanding of how the turbine blades will sulfurate, as all aero engines do. So that's the first step. The second one, which links into comprehending, is ultimately we envisage a world where the engine itself has an awareness of its own context. And as we'll see today with some of this technology, ultimately we see that the engine could potentially take action in and of itself to make decisions and take action that leads to a better outcome in terms of what that engine is achieving, either from a performance perspective or from an availability perspective. So that's connected. We're already making progress, either through looking at the intelligent engine pages on Rolls-Royce.com or through examples that we've been bringing to life this week. There is tangible progress in all of those areas. This one, for example, Taming the Volcano, talking about applying data analytics capability to moving from a world where we had to totally avoid volcanic ash to one of knowing how to model the effect on the engine and therefore being able to direct an airline to when they can and can't fly through certain concentrations of ash. This is key because if you forgive my pronunciation for a start, but think back to Eyjafjallajökull, the volcano in Iceland that erupted in 2010. That shut down airspace for a significant number of days, 20 countries, 10 million passengers, $4.7 billion of revenue apparently lost has been calculated. We can now be less binary and be more sophisticated in knowing when and how an aero engine can fly through volcanic ash. So a great example. At this point, I'll hand over to James to take you through a next tangible example of what we're leading on in the intelligent engine as we talk specifically about robotics.
Thanks, Richard. So, my name's James. I'm here to represent part of the business that we call Repair Technology, and the idea of our team is to effectively designing and developing new repair techniques to keep the engine flying out in service for until it needs to come back into overhaul. When it does come back into overhaul, we want to make sure that we can repair those things quickly and cheaply and get the device back out and servicing the customer as and when it needs to do so. So today we've got a couple of examples of the technologies that we are developing to help us service the engine when it's out in the fleet. So these are types of technologies that are robotic in nature, often enable us to kind of perform services like inspecting and repairing engines whilst they're still attached to the aircraft. So I can't stress that enough. We need to make sure these things get inside these inspection ports and actually perform kind of repairs and inspections whilst the engine is still intact and on the aircraft.
We get you a little closer to the microphone so we can hear in the back. That'd be great.
Yeah, sure. Is that any better?
Yeah.
Apologies. So this, in order to do what I just described, we've devised a technology supply chain of which we've got a large number of global partners that we work with regularly. That you see on the screen here. I'm not going to list them all off today, but we have got two representatives of the University of Nottingham in Dragos and Sebastian from Harvard University, who are going to show you some of the technologies that we've been developing today, and I'll go through some of those just now. So the first of those is a device that we call remote bore blending. And this is a technology that is enabling us to get inside engines and repair compressor blades whilst they are still on the engine. So the idea of this device is that it enables a person who's a skilled person to control the robot and actually perform a repair whilst the engine could be over the other side of the world. So this is a revolutionary service idea, and this is something that we'll take you through a video of in a second. Just before we get to that, just mention these things on the left-hand side of the screen. You'll see those for all of the case studies we'll talk about today. Basically, an objective of what we're trying to do, who we've got this funded by, and in this case, the Aerospace Technology Institute, part of the UK government, who we're working with, and in this case, that's the University of Nottingham, and the technology maturity level. So the technology maturity level is something that's kind of industry standard, introduced by NASA in the 60s. Goes from 1 to 9, with 1 being a kind of a crazy idea, 4 being you've developed and demonstrated some of these ideas and the key components of in a laboratory. Number 6 is where we have done a combined contextually kind of relevant systems engineering engine demonstration. We've actually started to develop these things and use them in real world. So without further ado, just quickly show you the first one. This is remote engine surgery, and again this is developed with the University of Nottingham. I'm just going to quickly show you why we're doing this. So this is the first thing, is that generally speaking these engines, they work out in service and often they can pick up some damage on the compressor blades. We send out skilled mechanics to go and perform those repairs, effectively with a long pole, and it's a lot of skill and it's a lot of time and effort. There's not many of those guys to go around, so we need to make sure they're in the right place at the right time. Or we get a relatively unskilled person to bolt on a robot, like you see to my left here, and that goes onto the side of the engine that anyone could bolt onto the side, and we as a skilled person can take control of that from somewhere like Derby, so as a central availability centre, and start to repair the compressor blades. So you see it here being introduced into the engine gas stream. You see the pictures on the left-hand side of the screen with the sharp end, effectively, of the device going inside. What we're doing here is generating a 3D point cloud, so that enables us to generate the types of trajectories that we require to actually perform the repair. So we should say this is a device that's been designed and demonstrated by the University of Nottingham. It started off as an idea we all had at about 3 years ago. We've gone from there to a full-scale engine demonstration within about 3.5 years. So we're all quite proud of this as a device, but it's basically allowing us to service our engines within hours rather than days. So it's potentially a revolutionary idea. So that moves us on to a project that we call Inspect, and Richard was just talking about the engine being contextually aware. And this is a device where we're suggesting that rather than just having ears on our engine health monitoring systems, we can have eyes on the health monitoring system. So it's allowing the engine to inspect itself potentially. So as you'll notice, this project is a slightly lower TRL level. It's not ready for service. It's something that we're working on in the background. It's funded by Innovate UK, and we're working with a group of suppliers and partners that you see on the left. But it's something that we're quite interested in as a kind of a new concept. The idea being the engine flies around with a set of effectively fibre networked cameras. Because they have to be thermally managed, because this is a very high pressure and high temperature environment. You can see one of the example devices you can see being deployed onto the side of the engine casing, coming into the gas stream, illuminates the object of interest, which you now see in the field in the centre. And that is, once the engine's rotating slow enough to actually perform an inspection, all of those bits of information are brought through to the EMU, engine maintenance unit, and is sent back to the availability centre, where we can actually start to suck in and bring in lots of useful bits of information. This is providing a more contextually aware piece of engine inspection hardware. Because it's a data-rich environment, it's basically a big sensor that we've got connected to all the engines around the world, potentially allowing us to open up a big avenue for big data environment. So the next one we've got here is an example of a pair of snake robots that go into the engine, not to remove material this time, like I showed you in the first example, but to put material back on. So there's a couple of different things we're trying to do effectively with all these different technologies: either inspect things better, remove bits of damage, or put things on. This is where we're trying to patch repair some coating. So this is a collaboration between a company called Metallisation in the UK and the University of Nottingham again, and this is funded by Aerospace Technology Institute. I'll show you a quick video. So, as I said, we have two snake robots. We're entering in through the combustion chamber. You see the first one here. I'm not going to go into huge amounts of detail, but effectively these are segments that are tendon driven with cables, and I'll let Dragos talk about that in more detail when we talk about this device. But the first one you see going down to the area there, we're inspecting the coating with a proprietary NDE technique, looking for any bits of delaminated material. The first snake robot is also then removing the material, removing the damaged parts, repairing the surface to allow for the second snake robot to come in place and do the coating redeposition. And all we're trying to do here is perform a patch repair. We're not looking to bring this engine back to kind of full health, making sure that it comes back in to the scheduled maintenance overhaul at the right time, not early, because that costs us money. And then those parts would be replaced when the engine is back to component level. So the final example I've got for you today is a revolutionary way of inspecting a large structure. So that structure we just showed you in terms of the combustion chamber is a relatively difficult thing to perform, because you're just basically pushing in with conventional techniques a big piece of spaghetti with a camera on the end. So if you or I to perform that inspection, that would take you a few hours to perform a mapping of that combustion chamber. We thought, rather than doing that traditionally, we could put cameras on the end of small walking beetles and have them work in a team, whereby I go and look in the far corner, another one of my colleagues goes and look in another corner, and collaboratively we start to map the whole environment. So this is one of our more sort of far-reaching technologies in that it's TRL2, so we've got a lot of work to do with this yet. Working with Harvard University on the actual structure for the walking device, but the University of Nottingham for how we get them in and out, and we're looking for funding through the EPSRC and NSF as a joint proposal. So that's something that's due to go live very soon, we hope, and I'll show you a quick animation of what we hope to achieve with that. So, as I said, we're going back into the combustion chamber, and the deployment mechanism, which is similar to the kind of things you will have seen previously, and if you go on the University of Nottingham website, you'll see other examples of these types of technologies that we've achieved and done engine demos of. But this is a device that's now kind of spitting out these miniature walking beetles. They can go off scuttling around, go to all the far-reaching different parts of the combustion chamber, and they're all throwing what they're seeing, their perspective, back to a central location. So it's then providing a bigger map like you see on the screen here. So it's a much more efficient way of performing the same kind of inspection. If we did it conventionally, it'd take us about 5 hours. If we did it like this, who knows, we could probably do that in maybe 5 minutes. So as I said, we bring them back in. We're not ever wanting to leave those things in place. That's obviously a very inconsiderate thing to do. We bring them back out and then send the engine back on its way. So that's 4 examples of some of the revolutionary technologies that we're developing with our partners across the world. A lot of these things aren't ready yet. We've got a lot of work to go in terms of to get them to be more mature. However, you will see some examples of some technologies like the one to my left, where we've actually done engine demonstrations and looking to be going live very soon. And I'm going to sort of now hand over to Royce and Sebastian to talk about some of the detail. So do you want to come and describe the landing robot?
Yeah. So my name is Royce. I'm a professor of manufacturing and director of Rolls-Royce UTC in Nottingham, University Technology Center. Yes. So what you have here is a robot which has been designed, everything, even inclusively the software, hardware, everything has been designed by Nottingham. And the idea is an skilled operator takes this robot and bolts it on the engine, and in that moment the specialist from Derby can operate remotely all the operations for repair. So we are not talking about here only inspection, we are talking about repair. So what does it mean? When an engine, for example, ingests some small stones, the blades might be deformed. So in order to release the stresses, what you do, you want to remove a piece of material from there. So what this robot does, after being bolted on the engine, there is this little probe, slender probe, goes into the engine, yes, in the gas stream, and scans. So we have a scanner there, takes all the cloud points, and after that identifies the damage. After that, the operator will decide which are the points where the blade should be repaired. And the second operation, the probe reposition itself against the blade, for example, and after that, with a high-speed spindle, start repairing. Everything is done by sending packages via the internet, secure internet, and basically that's it. At the end, once again, an inspection. So there is no need for anyone to be a specialist to be deployed around the world. So this is the first probe, such a probe in the world. Correct?
Correct.
I think it's right. Any questions later on? Yes, am I right?
Yeah,
later on.
Let's let Sebastian describe the small.
Thank you.
So just while Sebastian's setting that up, essentially what we're describing here is we've got one of the miniature walking beetles from Harvard University. This is representing just the walking beetle part of that. You will have seen or you will see eventually the whole concept tie up together with some snake robots that are going to come from the University of Nottingham. But are we going to put these things on the table?
Yeah, definitely. Cool.
Okay, so they don't have any cameras on them, they're kind of shattered.
Yes, exactly. Hi everyone.
Okay, so what I'm holding in my hand right here is one of the robots that we're talking about here. It doesn't look exactly as the render that we had before, but hopefully in a few years is what we're going to get. So this robot here has 4 legs, is bio-inspired, so we took inspiration from the cockroach to develop this over the past 8 years, more or less. It weighs 1.5 grams, is about 4.5 centimeters long, so it's some kind of concentrate of technology that we have here over the past 8 years to get this kind of robot here. Now, the context of this kind of robot, as James said before, is that Harvard obviously we're very interested in the research side of things. We want to see develop manufacturing techniques that allow us to start to build these robots at smaller and smaller scale. So what we've been focusing on are really the manufacturing techniques, and to do that we've been able to design a very cool set of robots, including this one here and others. But not only is our interest in the research side of things, but when we get these type of robots, we can start to envision applying these to specific applications. In this case, it's engine inspection. So this is not a finished product right now. It's still ongoing research, but we're hoping in the future to not only scale this down so that we can fit it in the end of bore scopes, but also start mounting cameras on them. Increase the number of sensors so that after we can really have this kind of intelligent behavior of a swarm of robots just like this one. I'll be very happy to give a bit more details on exactly how these works for the ones who are particularly interested, and I'll also have them demoing on the table here. So these are autonomous. I'll be able to show you a quick demo by switching them on, and they'll run a bit on the table here.
So I think just to finish before we run any Q's and A's and potential demonstrations of the robots, that's just to give you an example and a flavour for where we're taking this intelligent engine vision. It is not any particular product or service in our portfolio, it is a vision, it's a way of thinking, and I hope today what we've been able to do is show you some of the more visionary aspects. Our vision here is unbounded. We've got some early TRL activities, but these will accelerate through and really start to bring this whole concept to life. So with that, Oliver, is it Q&A? Okay, I'm happy to moderate any Q's and A's. Any questions? Yeah.
It's the reporting for the engineer. It all looks fantastic before through life engineering services, and fantastic cutting edge technology. It's a tricky one, but do you know if this is proprietary and unique to Rolls-Royce, or are other large engine manufacturers doing something similar? Can you get those technology?
On the particular robotics, in which case I'll hand over to James.
Yeah, so clearly we have a bit of competition in this field, but it's something that we know everyone's got different problems, so it's not like we're working on exactly the same thing each, but we know that of our competition, and we do know that there are sort of elements of the things that are similar, and I'd say we're probably on similar grounds in most cases. I would say everything we've shown you today will be unique to Rolls-Royce.
Any other questions? Yes. I believe, yes.
Can I get back focus? So the idea is that an inspection would have been performed. There would be a routine inspection that goes on all the time that's out in the world now. So yes, you would have seen and known where that damage is. But then these devices will have multiples of these things, you imagine, in kind of strategic locations around the world, around our on-wing services network. And they would be deployed to the site. That would be a lot quicker than sending someone from a central location. Yeah. No, so, whoops. This robot is capable of 3D scanning. It then sends the information back to Derby. We can then reconstruct that information, send a toolpath to the robot, which will then perform the repair, and then the subsequent inspection, all without having to remove the robot from the engine. So we've tried to remove the steps where we kind of take things off and put them back on. So an initial inspection to flag the damage. We know where it is. Send this to the engine, bolt it on, performs a 3D inspection, sends that information back. We reconstruct it, send a toolpath back. The robot does the job, performs another inspection to confirm that everything's okay. Then we take the robot off.
In terms of the why for that, there's two real reasons. One is to make better use of a scarce set of skilled resources. The second is to not have to take the engine off wing and disassemble it to perform its repairs. Any other questions? Had time for a couple more. I know at the back there was a hand earlier. So I'll answer the first bit. Depending on which fleet of engines it is, there will be a centre. So for our large wide-body engines, the data will go back to Derby, the data. But in terms of the deployment of the hardware to go and do this, then we'll position that strategically around the world. But the point is, as James said, that a relatively unskilled individual can perform the bolting on of the hardware, as opposed to have to be the skilled individual that chases the hardware around the world. That bit can be done remotely. We have different service centres for different fleets around the world, so not one central location, but there are several central locations. In terms of timescales, I'd hand that question over to James.
Yeah, so in terms of timescales, all of the projects we've shown you today are on different timescales. The thing we've got in front of you here is probably 1 to 2 years away from being really into production, and I should say also actually that some of the elements of this device have been used in the field already. Other things like the swarm robots potentially maybe more than 5 years away from actually seeing an engine even. So that's kind of gives you an idea of the flavour of the journey we have to go on to get these things to be more mature.
But I think the point is we're starting now. So one final question I've got time for. I know you had your hand up earlier, so I'm going to pick you out of the three.
Thank you. Neil Calder from Aerospace Manufacturing Magazine. What we've got here is something which is configured for essentially robotics based for repair operations. So materials processing, static kiosk environment. So does this match other actions that you've got going on for manufacturing, and do you see us transition between the two? Is there a set of capabilities that we're trying to set together that is going to go across initial manufacturing, virgin manufacturing, to remanufacturing and service?
So, James can feel free to comment, but I think the way I'd answer that is, there is, as James already alluded to, that you have constraints in terms of what you're able to do when it's a repair. You can't necessarily make it back to a brand new level of capability, but what you're doing is you're preventing the engine from coming off wing early. So the repair technology, in a similar way to any existing repair technology, you'll still have those challenges of getting as close to the original manufacturer as possible. The point about this technology is less about whether the repair is any better or worse than that. It's more about how you're saving the time and deploying your resource more efficiently to make sure the engine doesn't come off wing. So it's a different challenge we're addressing with this technology than the one you've alluded to, which will still remain a challenge we'll have to take on as well.